This is Craig Migliaccio from acservicetech, and I got a chance to go visit my good friend Bryan Orr from HVAC School. If you don't know who he is, you got to check out his content at hvacrschool.com and also his YouTube channel. So I got a chance to teach at his HVAC Night School Apprenticeship class using our PowerPoint presentations that we developed for HVAC teachers, which we have those for sale over at acservicetech.com. They're kind of like these posters right here, but now we're going to go ahead and check out the presentation. As we go through this, one of the things that I kind of realized when I was teaching in the high school, where I taught at a high school in Cape May County and also with the adult HVACR program there. And one of the biggest things that I always found was with the refrigeration cycle, that's going to give you the keys to the kingdom. And it's one of those things that people don't realize that they need and how much they need it, because what happens is when you walk up to an air conditioning system or a heat pump, you want to basically, with your measurements, be able to kind of like see what's actually happening in that system. And you're going to be able to do that based on your measurements. And if you know the refrigeration cycle enough, you're going to kind of picture what's actually happening. It's going to make your, not only checking the charge really quick with doing that, but also your diagnosis. You'll be able to tell real quickly if you have a low airflow problem or something like that. Of course, you're going to check your airflow, and that should be one of the first things that you check. But you can determine if you have a liquid line restriction problem or a low refrigerant charge or a low airflow problem very, very quickly, just based on your measurements and knowing this thing in and out. So what I found in the classroom was we started with a rectangle refrigeration cycle, and they'd say, Mr. Mig, you know, that's all fine and dandy, and I understand that picture, but it doesn't apply to real life, you know, and so that's why we started putting it onto an actual system. Right up here, you have your refrigerant states. So you have your low pressure, low temperature liquid indicated by your dark blue color. So this is while the system is running, and it's been running for, say, 15 minutes. And you have your low pressure, low temperature vapor, which is your light blue color, and there's little dots there. So you see that, and you see the high pressure, high temperature liquid, and that's the light red, and the dark red is the high temperature vapor, and that's where it exits the compressor at. And so we're going to start right here first, and over here you have an air handler. So the blower motor is sucking the air across the indoor coil, and right here you have a thermostatic expansion valve, and you have a little bulb right here, and that comes up the top of the thermostatic expansion valve. This particular one is a 2-rod. I know it's a small picture, so it's hard to see. This is kind of the older style. It's the non-balanced port, meaning that when you have real high temperature out here, what's happening is that the thermostatic expansion valve has a harder job controlling the superheat across the evaporator coil. We'll get into that in a little bit. And right here we have the outdoor air coming in, and then you have your hot air getting discharged outside. Of course, what's happening here is you're absorbing heat into the refrigerant inside the building. The refrigerant is moving that heat, and it's storing it, and it's bringing it over to the outdoor unit, and that's where you reject the heat out at. And so there's no such thing as cooling a building, even though you say cooling mode. It's, you know, your air conditioning mode, and what you're doing is you just are lowering the temperature inside the building. Of course, you're also taking the humidity out of the building by attracting it onto the coil. It drips down onto the coil and drips out to a place like outside. So here you have, in air conditioning mode, this coil right here is called the evaporator coil. And even if this was a heat pump, it still comes, it's called an evaporator coil. It's referred to as the indoor coil. This is the outdoor unit. If it's air conditioning only, you can refer to this as an evaporator coil. This is the condensing unit. What's funny about this is you can call it the condenser, you can call it the condensing unit, you can call it the outdoor unit. And so the condenser coils within the condensing unit. And so there's a lot of that terminology that gets thrown around. You just want to understand that if somebody's talking about the outdoor condensing unit, you know that they're talking about an air conditioning only outdoor unit. If you don't know what the outdoor unit is yet, you just refer to it as an outdoor unit until you can determine what it is.
Meaning whether it's a heat pump or straight cool.
Yes, whether it's a heat pump or an air conditioning unit. All right, so right here, this is the condenser, and the secret to refrigerant is the saturated state or the phase change. That's actually how the refrigerant is able to absorb heat here from the indoor air, and it transports it over to here. It's that phase change from from, in this case, vapor to liquid, and from here, it's liquid to vapor. That right there is the key, because the refrigerant's able to hold the temperature steady this entire time. And a good target temperature for the manufacturer that they designed this stuff to for air conditioning mode is 40 degrees. That does not mean that you would set the saturated temperature on the low side over here for 40 degrees. That's not correct. You really need to check the subcooling on the liquid line. But at this evaporator coil, it's able to hold it, say, at 40 degrees this entire time as the air, which is maybe at 70 degrees, is coming across the evaporator coil, and the refrigerant is just absorbing the heat, but it's not changing in temperature until it gets to here. And so then it can rise in temperature after it completely turns into a vapor state, and the increase in vapor temperature between here and here, that's called the superheat. And the thermostatic expansion valve is constantly controlling that. And you have the spring pressure, the external equalization pressure, and the bulb pressure. It's able to hold that constant. So anyway, the whole secret is the phase change. Because if it was only pure, just vapor here, meaning it's just a gas, like just like the air is a vapor right now. If it was just gas this entire time, you would have very little ability to absorb heat in from the building. So it has to go through a phase change, just like an ice cube is able to hold the water at 32 degrees until the ice cube completely melts, and then the water can change in temperature. It's a phase change. So right here is a compressor. This particular compressor is called a scroll compressor. So you can see the inside, but you have several different types of compressors you can run into in the field, and a lot of times for air conditioning units, it's a reciprocating compressor, which is an oval one. When you look down from the top, it's oval. And this one right here is a scroll compressor. This will be round and really tall. That's a scroll compressor. This one, a metering device. It could be a thermostatic expansion valve. It could be a piston metering device, which is a fixed orifice that has a chamber where you can open it up and replace the piston size, or it could be capillary tubes. I'm just kind of curious how many of you have run into indoor evaporator coils equipped with a capillary tube metering device, which is just a little, it looks just like this right here. That's all it is just that tube. And I'm not talking about the distributor tubes that connect the metering device to the coil, but has anybody seen indoor coils that only have that as the metering device? No? Oh, okay. Yeah, they're out there. They're out there, and so you run into that. That's a fixed orifice metering device. You could run into a piston metering device. Those are both fixed orifices, whereas a thermostatic expansion valve is a lot better for controlling the superheat across the evaporator coil in order to, if you're turning the thermostat on for the first time, it's able to reduce the humidity, reduce the heat load in the building real quickly. Whereas a piston or fixed orifice metering device, kind of like that, it takes a long time. Like when you need it the most, it's the least effective, right when you're turning it on for the first time. So we'll keep going here.
And that's a key thing to consider, is that it's not just controlling your TXV or your electronic expansion valve isn't just valuable when the system is running under normal conditions. It's also really helpful, the fact that it can go more wide open when you're in a hot pull down or when you're trying to bring the space down to temperature, which is also a nice thing. And in refrigeration, that comes up a lot.
Yeah.
When the fixed orifice is not as effective, it's because I guess the pressure drop is not as big as when you have the TXV.
So what happens when you have a high heat load in the building, say it's like 80 degrees, or maybe it's even 70 degrees, but it's real high humidity, what happens is the piston is not going to allow more refrigerant into the evaporator coil. Let me just back up for a sec. So it's going to, basically, if you have a piston here and you have a high heat load in the building, what's going to happen is this phase change is going to be smaller, meaning that piston is only going to allow the normal amount of refrigerant into this system based on the subcooling and the pressure, but it's going to be a lot smaller. And what that means is you're going to have more superheat. So if your refrigerant turns into a complete vapor here instead of here, the refrigerant's going to be passing through a lot more turns in the evaporator coil before it exits, and you're going to have a much higher superheat. Too high of a superheat, and what's going to happen is that's when it comes out right out here, and you're going to notice even, say, this at the service valve, maybe it's not even sweating, and it's all that type of stuff. Yes?
that also means that the evaporator coil is going to be hotter or not 40 degrees?
Yeah, it'll be a higher temperature. The saturated temperature may be higher, but really what it comes down to is the vapor temperature exiting this coil is going to be a lot higher than what it could be if it was more efficient. An efficient superheat, which is, so say this is 40 degrees all through here, and you have 70-degree air passing across this, and in this case we have a thermostatic expansion valve, so say we have 20 degrees across here, you're going to have 50-degree air coming out, and of course that's based on also an average humidity. If you have a high humidity, you may be lower than regular 18 to 20 degree delta T across the evaporator coil. But what's going to happen is this 40 degrees is going to stop even maybe right here. And then you're just going to have the vapor temperature. So if it's 40 degrees and then it starts rising, it's going to come out here. It could even come out the same temperature as the air coming across that coil. It could even come out as like, say, 69 or even 70 degrees. If it's like a huge heat load in the building, it's going to exit way hotter than it needs to be. And so this thermostatic expansion valve is going to be able to open up and allow more subcooled refrigerant. It's going to lower the temperature because of the pressure reduction, but it's going to allow more refrigerant in here. It's going to hold the superheat, so maybe it's 52 degrees here instead of 70 degrees here. And so you got to think if it's a lower temperature refrigerant that exits the evaporator coil, it's going to be a lower temperature air that's going to exit through the supply plenum. Does that make sense? Or it might not have been a great explanation. I don't know. Go ahead.
I mean, it does. It's just basically you're allowing more liquid into the evaporator coil.
That's correct.
So you keep less vapor in the evaporator.
Yes. Yes. You're allowing more refrigerant into the evaporator coil to absorb the heat load while keeping the superheat constant. You know, maybe average superheat for a thermostatic expansion valve might be 8 to 12 degrees, you know, if it's operating correctly with a correct charge and an average heat load, but you may get 14 or even 16 degree superheat across that evaporator coil based on that thermostatic expansion valve.
Yeah, like we talked about the other day, you have to think about the temperature of the refrigerant in the evaporator. That's our saturated suction temperature, our evaporator temperature. But you also need to think about how full the evaporator is. And superheat tells us about the fullness of the evaporator in terms of the boiling refrigerant. Again, it's boiling refrigerant that effectively removes heat from the air that's passing over it.
So I tend to call this a saturated state, but it's a phase change from liquid to vapor. All right, so what's happening? You're separating the low side from the high side, and really it starts at the compressor. You have low pressure, low temperature, superheated vapor entering the compressor. The compressor is increasing the pressure, which therefore increases the temperature. So if we look at this bottle right here is static right now, and so basically it's in the saturated state because there's liquid and vapor in this tank, and since you have both of them, it's saturated. And so what you do is you take the pressure and you bring it into the inner ring on a compound gauge like this, and this is R410A. And so on this one, it says that it is 227 psig. You bring that into the pink inner ring. Pink is R410A. And you see it reads about 78 degrees. Now, this is higher than the temperature in the room right now. So there's actually a little bit of air in there. It's either that or this compound gauge was not calibrated on 0 before we connected it.
That was my responsibility, so it's likely that it wasn't.
No, I think I opened the handle before checking, but I'm pretty sure they were at 0. So this temperature meter right here says it's 70 degrees inside. That bottle should be at 70 degrees saturated temperature for R410A. It has too high of a pressure. I would not reuse that refrigerant, and I can confirm that because this was in this room for several hours, you know, before we even got here, and so it was at a steady temperature. So that's how you check a recovery bottle in case you don't know what refrigerant's in it, and to tell if it's contaminated with air. And that happens from a loose hose connection when you're recovering the refrigerant out of the system. That's usually what happens. Even if you tighten them and maybe the vibration of the recovery machine or something like that gets it loose, or maybe you just want to check all that, and you want to purge the air out of the recovery machine. And some people vacuum the lines there. But basically, you got to get all the air out of the system before you recover the refrigerant into a recovery bottle. So 70 degrees here. So if this system was off, you'd have saturated refrigerant throughout this whole thing. And if it was 70, this is a like perfect example, right? The 70 degrees outside and 70 degrees inside, that's rare, for a split system, but just say it was, then you check the pressure on the ports, and it should convert to the saturated temperature of 70 degrees for R410A, and that just confirms that you have R410A in this system. So it's all saturated when it's off, unless you have a hard shut-off TXV. It's going to trap the subcooled liquid, there, so that when it starts back up again, it already has liquid fully in this line right here. And so basically you have the compressor locked and shut right there when it's off. And so there's always going to be a pressure or stop basically right there. So from here to here, it's going to trap and not allow equalization of the pressure across the thermostatic expansion valve for a hard shut-off TXV. And that's just for the next time when it turns back on again, it wants to get the subcooled liquid into the thermostatic expansion valve immediately instead of waiting over time. And I will tell you, in the field, when I started, I didn't go to a school. I just learned in the field. So this whole thing took me several years to understand. And that was on my own. And then when I got in the classroom, I had to go and do all my testing on my own to say, okay, I was doing all this stuff for years, but how do I communicate that to the students? And I was like, darn, if I'm going to tell them something that's wrong, at least to the best of my ability, I wanted to stay after, and I was doing all kinds of experiments and kind of trying to figure things out to try to communicate this stuff as best as possible. But yeah, this stuff takes a long time. So, any questions so far? Now, while the system's running, the phase change occurs in the condenser coil and in the evaporator coil. And you have a low side and a high side. The compressor and the metering device are what separate the high side from the low pressure side. So this whole thing is governed by pressure, but really all you're concerned with the operation is temperature. So you could potentially assess the whole system just based on temperature without hooking the gauges up, but the problem is you'd have to locate your temperature probe in the middle of the saturated state in this coil here, and you'd have to get it in there in a good place. And so if you're trying to check your subcooling, you need a temp sensor in the middle here and a temp sensor here. Same thing, in your evaporator coil, you'd have to take the evaporator coil cover off and find where you believe the saturated state is going to be at and put a temp probe. That's why we don't do that. Very time consuming. There's a chance for error there. We check the pressure and convert it immediately to saturated temperature. And so, but the whole point is that we're operating based on temperatures. So a lot of times people ask me, that's great, I don't care about your subcooling and your temperatures and stuff. What pressures does it run at? I'm like, man, I can't tell you because it depends on the day. You could totally overcharge a system and it's not going to perform effectively because you just overfilled this whole condenser coil. When you overfill this, the pressure out here is going to be dramatically higher, and you're going to be drawing a lot more electricity because the whole thing is filled. And so you're going to have way too high of a subcooling, but you're also going to have way too high of a pressure. If you don't put enough refrigerant in it, you're going to be starving the thermostatic expansion valve that's in the inside here. This evaporator coil says TXV installed, so some technicians take out the TXV. So you don't want to just go by that. You want to actually look inside the evaporator coil box and see the metering device inside, because some people, they don't trust the thermostatic expansion valve. Well, and that's all because the head, that would rust, and so you would leak refrigerant out of the top, and the bulb would no longer be any good. And so the bulb is mounted right here, and so the bulb would not apply opening force to the thermostatic expansion valve. And so a lot of TXVs got a bad rap because this was just standard metal, and a lot of the newer ones are all stainless steel. And so a lot of old technicians may not trust the thermostatic expansion valve, but that's the norm out there for these systems. And I see inside this one, we have an outdoor thermostatic expansion valve, and this one has a stainless steel head on that, and it's welded there. As well, the bulb is no longer copper, and the line is no longer copper on a lot of new systems because all that stuff breaks. It rubs, it vibrates, you lose the charge once again. This copper bulb, may have got squeezed or something, and there's a problem with that. So all this stuff is now stainless steel, and you don't really have the similar metal connection between stainless steel and copper. They work pretty good together, so that's why You can clamp it there as well. Some people may not recommend this, but you can use a standard stainless steel, like kind of garden hose clamp to mount these. The problem with that is people stay away from it because you could accidentally over tighten the bulb onto the tubing and crush it, and then you're going to end up with a leak. But you want to make sure that that bulb has good surface contact. Anyway, low pressure side right here, it's highlighted in yellow while the system is running. Highlighted high side while it's running. Before you check a refrigerant charge, you want to allow, say, 10 to 15 minutes of runtime. If it has a thermostatic expansion valve like this, you can get away with 5 to 10 minutes. If it's a fixed orifice, you want to allow that 10 to 15 minutes. Really, you want to allow the 15 minutes to occur, and you should have 70 degree or higher air temperature outside, and at least 70 degree air dry bulb temperature on the inside of the building before checking the charge. You don't want to check the charge when there's not a heat load in the building and the indoor temperature is going to fall dramatically, below 70 degrees. There's ways that you can fool the outdoor unit, almost like into thinking. There's no logic in reference to this computer board wise on the standard systems, but you can fool the outdoor unit into thinking it's a higher temperature than what it actually is by putting a charging jacket or putting a piece of plywood across here to block the airflow, and then try to get the increased saturated temperature to a higher temperature. Let's just go to the basics here. Low pressure enters the compressor. High pressure exits the compressor. Since it's high pressure, it also increases the temperature. Like that's what I said. It's not necessarily about pressure, it's about temperature. So as it's flowing through here, it's flowing through the coil, right through this coil. It's rejecting heat to the outside air. It's then lowering in temperature because it's in the vapor form, like a gaseous state, until it gets to right here. And that's when you are turning into the saturated state. And once it hits this point where you have liquid and vapor exist at the same time within each of the tubing runs, it's going to stop falling in temperature. It's going to stabilize. And so that might be maybe at, say, 100 degrees. Maybe it's a 100 degree saturated state as it's flowing through here. And then once it comes out over here, it's still 100 degrees. 100 degrees, 100 degrees, 100 degrees, 100. By the time it then comes over to here, it may be 90. So 100 degrees right here minus the line temperature of 90 degrees gives you a 10 degree subcooling. So this right here is where it changes out of the saturated state into a complete liquid. Once it turns into a liquid, that's when it can start falling in temperature, and here we have subcooling. The temperature lowering of the refrigerant from here to here. You may ask, how do you measure that? Really, you just take a pressure measurement right here. You convert that to saturated temperature on your gauge face using the Danfoss refrigerant slider app, using a digital manifold gauge set. Any type of calculator you have on your phone. But basically, you're measuring your pressure at the port right here. You're converting that to saturated temperature for whatever refrigerant's inside this unit. You need to know that beforehand. So say it's R410A. But what it's going to tell you is going to tell you the temperature right here. I know it sounds odd because it's a distance away, right? It's flowing through all this, and then it's coming over to here. Your line temperature is going to be lower than your saturated temperature at the port. And that change in temperature, that's your subcooling. So really, even though you measure your pressure here, you're measuring your saturated temperature in the middle of this outdoor coil. It gets even stranger when you talk about the evaporator coil, because when you're measuring your pressure, your low pressure side, you're measuring your pressure here and converting it to saturated temperature. And really, you're trying to figure out what the temperature is in the middle of this coil all the way over here, maybe 50 feet away, 75 feet away. And so then you take a line temperature here, and the line temperature is going to be higher than your saturated temperature here. That's called your total superheat because there's no port to measure. Oh, I'm sorry, there's no port to measure over here usually on a standard system. So this will be superheat if you measure your pressure and temperature here. But since you measure it out here, it's called the total superheat. It takes into any consideration of this tubing running in the ground or pressure change just due to maybe a high vertical run or long line set. So any questions so far?
I have a question.
Yeah, go for it.
So I recently installed some split units, right? Split systems. I was working on these condensers, and the tag says that you're supposed to charge them with 11 subcooling.
Yes.
So I was wondering, because depending on the outdoor temperature, the subcooling changes, right?
Yeah, so within a normal temperature of, say, 70 degree outside to 90 degree outside, it's going to be pretty close to that 11 degrees of subcooling for your target. That's not going to change. Now, when a manufacturer gives you one target subcooling rating that's on here, that's basically the average of, from 70 degrees to, say, 110 degrees. And so if you're lower in temperature, it may be 10 or 9 degrees. And if you're up at 110, it may be 13 degrees as your target subcooling. But they just give you one to simplify it. So some manufacturers give you a chart where you open up this shroud and it tells you, based on the temperature outside, what the subcooling should be, the target subcooling. Does that answer the question?
Yes, yes. So based on whatever they give me, it doesn't matter. It's going to be a huge...
It's not going to be real far away from that. Okay. Yeah, that's going to be the average, and it depends on the day in which you check it and the heat load on that day. But that's why they just give you one to simplify it. Some give you three, and they're not off or very far away from each other, 1 or 2 degrees off of that one in the middle. Okay. Yeah. A lot of times the target subcooling, especially if you don't have a rating plate, it's going to be anywhere between 8 and 12 degrees of target subcooling if you have a thermostatic expansion valve. That's usually the norm, and I have seen at anywhere from, say, 8 to 14. I've seen as high as 19 degrees as a target subcooling posted on the rating plates of some systems. That's the highest that I've seen. All right, so anyway, you have your subcooled liquid refrigerant coming through the liquid line service valve, and then it comes over through the filter dryer, and there should be no change across the filter dryer. If there is a change across here, it might be very, very minimal, like maybe half a degree or something like that across it, and that's just due to the surface area of the filter dryer itself to the environment surrounding it. But if there's a huge pressure change or a lowering of pressure, which is also a lowering of temperature, then that filter dryer is clogged. And a lot of people argue about what that number specifically is. It's 5 degrees, it's 6 degrees, it's 3 degrees. I mean, it's just use your common sense, and always, always, always make sure your temperature meter is calibrated. Put it in ice water and check it every once in a while. Put both of them in. Anytime I start up my wireless probes, I put them together, like right next to each other, turn them on, and also my pressure sensors. Make sure everything is reading 0 psig and whatever the temperature it is outside. If you have some huge difference between them, it's going to throw off everything else that you're going to be doing. So always make sure they're calibrated and working well. So that comes down to everything. It's having trust in the tools, making sure they're calibrated, and make sure you know how to operate those tools. It's not great if you're constantly changing tools all the time, and that's for anybody, for me, everybody. If you got to get confidence in the specific tools that you use, because if you're switching all the time, I guarantee there's going to be issues, and then you're going to get confused during your troubleshooting. Why is this not working correctly? And then it comes right back down to you didn't check the tool ahead of time. Anyway, so you have high pressure, high temperature liquid refrigerant entering the thermostatic expansion valve. The metering device, whether a piston, capillary tube, so those are both fixed orifices, or a thermostatic expansion valve, they're all lowering the pressure of the liquid refrigerant. And when you lower the pressure of the liquid refrigerant, as soon as it enters this evaporator coil right here, what's happening is there's an availability of space now. So there's extra space. And so it's not just going to be liquid. You're going to have maybe around 20% as a flash gas, a gaseous refrigerant. And the rest is all liquid. So you immediately enter the saturated state or the phase change immediately after the metering device. And so you're absorbing your heat right away, whereas like where it comes out of the compressor at, you're in the vapor state, then the saturated state, then the liquid state. Well, here at the evaporator coil, the TXV is a pressure reduction device, and you're immediately into the saturated state or the phase change, and then you just come out as a vapor, and then increase in temperature as a vapor. All right, so evaporator saturated state begins. It's kind of, it's saturated. Saturated may not be a state, but it's saturated. So right here, this whole thing is saturated, and we talked about this before. Just say it's 40 degrees. It could be 36 degrees. It could be 44 degrees. That has to do with the liquid pressure of the subcooled liquid refrigerant and the indoor heat load. That will change your pressure. And remember, you're checking your pressure out here. So when somebody asks me what pressure it should be, I already know. I already know what's going on in their mind, meaning that we got a lot of work to do. You got to stop talking about pressure and think about saturated temperatures and line temperatures. And then, once again, the crazy thing about this is, this is not a joke at all. You will have your gauge set on. You will have your 2 temp meters on. You will be reading your superheat, your subcooling, and you see your low side sat and your high side saturated temperature. You can picture all of this happening. It makes it real quick for your troubleshooting. You don't have to add refrigerant into the system to see, hey, is my vapor pressure, is it now increasing because I'm adding refrigerant? No, you can figure out if it's a liquid line restriction or correct charge, undercharge, low airflow, those types of things. So it comes out of the phase change, and it turns into a complete vapor state, and then it's increasing in temperature. So this is the vapor, which is the gaseous refrigerant. It's increasing in temperature based on the heat load. If you ever have a system running and the vapor pressure here converted to saturated temperature is higher than the indoor temperature, you have a problem. And it's probably leaky valves on a reciprocating compressor or internally leaking reversing valve on a heat pump. It cannot physically be higher in saturated temperature than the temperature of what it is in the building. It can't. So that's like a telltale, hey, we've got a problem with the compressor, or it's your tools, or it's a reversing valve. So just keep that in mind, because the refrigerant is only going to rise in temperature somewhere below what the actual temperature is in the building. If you are low on refrigerant, the vapor saturated temperature where it exits the evaporator coil and where you measure it here, it may be the same exact temperature as it is in the building if you're low on refrigerant. And it's just because you just have such a little amount of refrigerant that the vapor is coming out here the same temperature, but and when I say that, I'm talking about your line temperature, but your saturated temperature, if you're low on refrigerant, you may be below freezing, and your evaporator coil itself is freezing over because the refrigerant inside is so low of a pressure and so low of a saturated temperature. So low refrigerant charge is a low saturated temperature, but an extremely high vapor line temperature. Does anybody have any questions on that?
What if, you can never have 32 degrees saturation, because then you're going to freeze the moisture on the air, right?
Yeah, on the evaporator.
As long as you're above that, you're good, right?
If you're above it, you're good, but you want to make sure that you have the correct amount of airflow. So you're thinking anywhere from 350 cubic feet per minute to 425 cubic feet per minute blowing across here for every 1 ton of air conditioning. But basically, say this was a 2-ton unit, it's 24,000 BTUs, you're going to need 800 CFMs, roughly 400 CFMs per ton, coming across this evaporator coil to have the correct amount of airflow. And that has to do with applying the heat to the outside of the coil for the refrigerant to absorb. But say it's 32 degrees, right? Or say it's 33 degrees, saturated temperature here. And the day that you're checking it, it's like 100 degrees outside, and it's 76 degrees inside. That coil's going to freeze. Once the indoor temperature lowers, that coil's going to freeze. You still have a problem there. Something's not right. So the manufacturers are designing roughly the saturated temperature to be around 40 degrees, but it doesn't mean it's going to be that way. Anybody else have any questions?
Well, that's just like the liquid line temperature cannot be lower than the ambient temperature.
Yes, exactly. Yep. Good. All right, so this is called the superheat right here. You have the temperature increase in the vapor refrigerant as it goes through the evaporator coil. Then you have, this is called the total superheat, going from here to here. And of course, when you measure your pressure here, you're finding your saturated temperature in the middle of the coil, and then you have the line temperature right here. That's called the total superheat. We use total superheat to check the refrigerant charge of systems that have a fixed orifice metering device. So you might have one capillary tube, or you might have 2 or 3 capillary tubes, but you will see that there's no piston chamber on those. Or you may see a piston chamber, and when you see multiple of these, they're called distributor tubes, and they're usually bigger than a capillary tube metering devices. Anyway, so then the cycle starts all over again. So I hope you got something out of that long presentation, and big thanks again to Bryan Orr for inviting me down to Florida and to teach at his HVAC apprenticeship class. And if you want to learn more about what he's doing, make sure you check out his website over at hvacrschool.com. He's got a lot of good resources, and he's always putting up new content. That's great. And also make sure you check out and subscribe to his YouTube channel. And if you want to check out our website, we have a bunch of resources there, such as our refrigerant charging and service procedures for air conditioning book. We've got quick reference cards. We've got PowerPoints for teachers. We've got posters just like these. So make sure you check all that out at acservicetech.com. Hope you enjoyed yourself. We'll see you next time at AC Service Tech channel.